Chapter 15, the Reactivity Series. Part 1. In the Reactivity Series, metals are arranged from the most reactive to the least reactive. To determine the reactivity of different metals, we observe the reaction of each metal with cold water, steam, and hydrochloric acid. Only the most reactive metals will react with cold water, while the less reactive metals will react with steam or hydrochloric acid. The least reactive metals will not even react with hydrochloric acid. The reactivity of each metal can also be determined by the vigor of the reaction. Reactivity series from most reactive to least reactive metal: potassium, sodium, magnesium, aluminium, carbon, zinc, iron, lead, hydrogen, copper, silver, gold. Metals at the top of the reactivity series, like potassium, sodium, calcium, and magnesium, react with cold water. The products of the reaction are metal hydroxide and hydrogen gas. The vigor of the reaction decreases from reacting explosively for potassium to reacting slowly for magnesium. Metals below magnesium do not react with cold water. Further down the series, metals like aluminium, zinc, and iron will react with steam. The products of the reaction are metal oxide and hydrogen gas. The vigor of the reaction decreases from reacting explosively for potassium to reacting slowly for iron. Metals below iron do not react with steam. Further down the series, metals like lead will react with hydrochloric acid. The products of the reaction are salt and hydrogen gas. The vigor of the reaction decreases from reacting explosively for potassium to reacting slowly for lead. Note that when lead reacts with hydrochloric acid, the salt formed is lead 2-chloride, which is insoluble in water. The formation of an insoluble layer on lead prevents it from further reacting with the acid, causing the reaction to stop before the reaction is complete. Metals below lead do not react with hydrochloric acid. Hydrogen in the reactivity represents hydrogen ions present in acids. It serves as a marker to indicate that metals below hydrogen do not react with acids. Part 2. Using the reactivity series. The reactivity series is related to the tendency of a metal to form positive ions. Reactive metals tend to form positive ions easily by losing electrons and forming compounds. Unreactive metals prefer to remain uncombined as atoms of the element. There are 3 ways in which we can use the reactivity series. Number 1. Predicting metal displacement reactions. A more reactive metal can displace a less reactive metal from its salt. For example, when iron is added to a solution of copper 2-sulfate, iron would displace copper to form copper metal and iron 2-sulfate. This is because iron is a more reactive metal than copper. The reaction will give rise to several observations, such as the appearance of a pink or reddish-brown solid, which is copper metal, and a color change of the solution from blue to pale green. The color change is due to the metal ions in solution changing from copper 2 ions, which is blue, to iron 2 ions, which is pale green. Similarly, a more reactive metal can displace a less reactive metal from its oxide. For example, when zinc is reacted with copper 2 oxide, zinc would displace copper to form copper metal and zinc oxide. This is because zinc is a more reactive metal than copper. Number 2. Predicting the reduction of metal oxides with carbon and hydrogen. In the reactivity series, metals below carbon can be obtained by reducing the metal oxides with carbon. For example, when copper 2 oxide is heated with carbon, copper metal is produced together with carbon dioxide gas. In the reactivity series, metals below zinc can be obtained by reducing the metal oxides with hydrogen gas. For example, when lead 2 oxide is heated with hydrogen gas, lead metal is produced together with steam. Number 3. Predicting the thermal stability of metal carbonates. Metal carbonates can decompose on heating to form metal oxides and carbon dioxide gas. The decomposition of metal carbonates can be detected by attaching a delivery tube that leads to lime water. The formation of a white precipitate in lime water indicates the production of carbon dioxide gas and hence the breakdown of the metal carbonate. The stability of the metal carbonates towards heating is related to the reactivity of the metals. The more reactive a metal is, the greater the thermal stability, or the more difficult it is to decompose its carbonate by heat. Hence, the carbonates of the most reactive metals, like potassium and sodium, do not decompose on heating. Carbonates of least reactive metals, like silver, decompose to form oxides of the metals, which will further decompose to form the metal. Part 3. Extracting metals. Most metals are found in nature, combined with nonmetals like oxygen and sulfur. These compounds are called ores. The more reactive a metal, the more stable the compound or ore is. Hence, it is much more difficult to extract sodium metal from its ore than it is to extract copper metal from its ore. With reference to the reactivity series, metals below carbon can be extracted from their ores by reduction with carbon, which is by heating the metal compound with carbon. Metals above carbon can only be extracted from their ores using electrolysis, which is by using electricity to break down the molten metal compound. Part 4. Rusting. Rust is hydrated iron 3 oxide, which is a reddish-brown solid. For iron to form rust, both oxygen and water must be present. The presence of sodium chloride and acidic substances also speed up rusting. Rusting can be prevented in 3 ways. 1. By placing a protective layer around iron. Examples include painting, greasing, covering with plastic, and electroplating with tin or zinc. 2. By attaching a more reactive metal, like magnesium or zinc, to iron. This method is called sacrificial protection. In the presence of oxygen and water, the more reactive metal, or sacrificial metal, corrodes in place of iron. Sacrificial protection is useful with large iron objects, like ships and underground pipes and tanks. 3. By forming an alloy such as stainless steel. Stainless steel is produced by adding chromium to steel. Chromium reacts with oxygen in air to form a layer of chromium oxide, which acts as a protective barrier. End of chapter 15.